Okay, so let's start. Welcome everybody come here to my presentation. This project is for my PhD program in the Ohio State University. My name is Tao Dai, and my advisor is Professor John Leopold. And the sponsors of the project are Cameroon International and Accused Technological Services. The project is dedicated for the solution of the problem surface stress cracking in oil industry. This is an oil platform, and beneath this oil platform, a huge subsea architecture was built to extract and transport crude oil from the subsea area to the surface of the ocean. And Cameroon International is oil field service company building the subsea components. For example, like the connector, it is partially cladded. It is fully cladded in the inner surface of the inner surface. Yeah. Another type of equipment they built is this one. This type is only partially cladded in the sealing area. This area is connecting the pipes. In order to prevent the leaking, so they make the 6-5 overlay there. But such equipment still face the problem of surface stress cracking. When the four conditions are met, this equipment faces the problem of surface stress cracking. The susceptible microstructure near the interface between 6-5 and the F22 steel. The second condition is the tensile strength. Tensile stress introduced by the crude oil transporting through this equipment, and the hydrogen from the crude oil is the third condition, and the fourth condition is the ambient temperature in the subsea environment. So what is the surface stress cracking? The surface stress cracking is actually one type of hydrogen-assisted cracking. The features of the surface stress cracking are the first one is the hydrogen atoms in the hydrogen surface stress cracking are from the cathodic reactions. There are two cathodic reactions here. The hydrogen sulfide obtains the electrons to form the hydrogen atoms and the sulfide species. The sulfide species can prevent the hydrogen atoms to form the hydrogen gas and also promotes the penetration of the hydrogen into the components. So that's the problem of surface stress cracking. So how can we reduce or minimize this problem, surface stress cracking? We usually use the post-weld heat treatment, but we have a dilemma of the post-weld heat treatment on the two types of dissimilar metal welds. These two types of dissimilar metal welds is the focus in our project. The first, the 6-5 overlay will be made on the steel components, and the heat valley zone will form because of the welding, heating, and the cooling process. The heat valley zone has very high hardness, and the NIST standard requires that the hardness in the heat valley zone should not be above 250, and so the post-weld heat treatment is required to reduce the hardness and also relieve the stress. But the problem is here. The post-weld heat treatment actually will cause the diffusion of the carbon from the steel side to the nickel-based alloy side. So the carbon will pile up in a very narrow region adjacent to the interface, and the hardness in this region will increase. Usually, previous researchers thought that the region with high hardness should be the planar growth zone. But in my result, this is another story that's different, and I will tell you more later. And because of the high hardness in this region adjacent to the fission boundary, the hydrogen-assisted cracking or surface stress cracking probably occur in this region. So it seems that the post-weld heat treatment is not the perfect way to solve this problem, surface stress cracking. But so we need to go deeper to study the effect of post-weld heat treatment. So we need to determine the post-weld the effect of post-weld heat treatment on the hydrogen-assisted cracking susceptibility of the dissimilar metal weld. We also need to determine the effect of post-weld heat treatment on the surface stress cracking of the dissimilar metal weld in the H2S environment. The third objective is to determine the optimal post-weld heat treatment conditions, which minimize the cracking susceptibility of the dissimilar metal welds. The fourth is to establish a correlation between the hydrogen-assisted cracking behavior and the surface stress cracking behavior using the delayed hydrogen cracking test. This is a cracking test developed in our university, Ohio State. And the last but not least is to determine if the hardness limit imposed by NACE for carbon non-alloy steel is overly conservative. There are two types of base metal in the project, F22 and 8630. F22 has only half of the carbon content of 8630, and it contains more chromium and molybdenum content, the carbide formers. And the filler metal is 625. The welding parameters are shown in this table, and the welding sequence is shown in this figure. And this welding was performed by Acute Technological Services. Yeah. This slide shows the welding coupons of the dissimilar metal welding coupons, And the samples were cut from this section, and after polishing and etching, we did the optical metallography work, and we showed the very typical microstructure near the fission boundary. This is a so-called discontinuous partial mixed zone. It's a fusion boundary section with a swirl structure, and we can see the His value zone, the cellular dendritic region, the swirl, and the planar growth zone, or called the fitness zone, because it always has no fitness feature. It's always white after etching. This section is a continuous partial mixed zone because there is no swirl structure. The planar growth zone should be a susceptible region for cracking because the EDX analysis shows that there's a sharp composition gradient of iron, nickel, and chromium across this planar growth zone, and the A3 temperature could be lower due to the nickel content in this area. So the virgin martensite probably forms when cooling down from the post-weld heat treatment if the A3 temperature is even lower than the tempering temperature. Some other microstructure. This is type 2 grain boundaries. This boundary possibly facilitates the propagation of the cracking, and in future cracking tests, I will compare the cracking path or the fracture morphology with this microstructure. Another very interesting discovery is the grain boundary here in the base metal. We can see the grain boundary. And the grain boundary in the base metal can actually extend into the planar growth zone and even extend into the cellular dendritic region. So we can conclude that this is epitaxial grain growth, and the planar growth zone probably has the similar crystal structure with the base metal. It should be ferritic structure. Next, the ACM backscattering image reveals more detailed microstructure near the interface. Yeah, here's type 2 grain boundary, I just said. There's a swirl structure, and we can also find some solidification grain boundaries. For the 8630, 625 dissimilar metal weld, we can also find some finger structure. It's the penetration of the filler metal into the base metal, and some nitration effect along the type 2 grain boundaries. And we can even find some precipitates occasionally in the planar growth zone, because in the hydrogen environment, the hydrogen tends to trap in the near the interface between the precipice and the matrix. So that's could be a susceptible region for hydrogen-assisted cracking. hardness test was done. This is the hardness map of the as welded condition, as welded samples. The highest hardness is up to 430 HV, and so definitely we need to do post-weld heat treatments to reduce the hardness, right? And some part of the heat value zone has lower hardness, much lower than this one. This is because of the tempering effect during the multiple beads welding process. The later beads will temper this region to reduce the hardness. Yeah, the post-weld heat treatment was conducted to reduce the hardness in the heat value zone, the different post-weld heat treatment conditions. We tried at least 5 different post-weld heat treatment conditions, and we can see the temperature, time, and the Holloman-Jaffe parameter. For those who do not know the Holloman-Jaffe parameter, it's a parameter synthesizes the effects of temperature and time in a tempering process. This is an equation to calculate the Holloman-Jaffe parameter. We also recorded the highest and average hardness in this tempered heat value zone. Plot the hardness with regard to the Holloman-Jaffe parameter, we can see the linear decrease. Very good result. For the F22-625 samples, we did the same, similar post-weld heat treatment. And we plot also, we recorded the hardness and plot the hardness with regard to the Holloman-Jaffe parameter. The hardness also decreases, but there is secondary hardening effect for the F22 still, because F22 has higher carbide formers like chromium and molybdenum, I just said before. Yeah, because the weakest hardness or nano-hardness cannot review the hardness in a very narrow region, like 10 to 50 micron, like the planar growth zone, that is too narrow. So we need to use the nano indentation to review the hardness in that very narrow region. For the nano indentation, either the maximum load or maximum displacement can be preset. And our samples were polished to 0.5 micrometer with the colloidal solution to keep the surface flat and smooth. And this is a load displacement curve. This has 2 stages, loading stage and unloading stage. The unloading curve goes back a little bit because of the recovery of the elastic deformation. And this is a record of the Young's modulus with displacement at each indent. This figure shows the indent size compared to the nano indent size. Here, the triangle shape. This is a weakest hardness indent size. The maximum displacement for this indent is 500 nanometer. Weakest hardness, the load is 100 gram. We can see the big difference of the the hardness size, the indent size. But the nano hardness is in the units of gigapascal. So we need to convert the nano hardness to the weakest hardness. Theoretically, there's a relationship that the nano hardness can only be multiplied by a constant 92.7 equals weakest hardness. But there's some size effect on the hardness, so we cannot use that simple equation. So we did some calibration between these 2 hardness, select 5 to 10 locations of the sample to make the nano indentation first, and then make the weakest hardness indents on the exactly the same spot. Then distance between the labeling spots should be about 200 micrometer. Then we compare the pairs of the hardness values and plot the weakest hardness and the nano hardness. And it shows that the relationship is a very good linear relationship. So we can use this linear relationship or the equation to convert the nano hardness to the weakest hardness. So after converting the nano hardness to the weakest hardness, Yeah, first we made 5 nano-hardness lines across this fusion boundary. And converting the nano-hardness to the weakest hardness, we can see the hardness distribution across the fusion boundary. This is a very narrow region. You see, it's only maybe 20 to 30 micrometer width. But we can still see the clear hardness peak here. The hardness is 550 HV. That's very high hardness and very susceptible, should be very susceptible to the cracking in hydrogen environment. We also can do the hardness map, nano-hardness map. This is a hardness map of 8630-625 sample. This is another map on the F22-625 map, F22 and 625 sample. This map corresponds to this area. We etched we just etched this area, the indented area. This is the microstructure of the indented area, overlap with the map here. We made some very interesting discovery. The previous research thought that the highest hardness should be in the planar growth zone or adjacent to the fusion boundary or the interface. But in our results, we found that the hardness peak is actually beyond this fissionless zone. It's as the initiation of the cellular dendritic region. It's very interesting. For this F22-625, the planar growth zone is very narrow, so maybe it's hard to tell the exact region of the hardness peak. But I still believe the hardness peak should be as the edge of the planar growth zone and as the initiation location of this cellular dendritic region. I think this is very new result. The nano-indentation can also record or measure the Young's modulus. So we can also make a Young's modulus map in a certain area. And we can calculate the strain. This is elastic strain equals the elastic stress over the Young's modulus. If we assume the stress equals 1, so elastic strain is 1 over the Young's modulus. So we will use this equation. We can also calculate the elastic strain map. Why do we focus on this elastic strain map? Because in future I will do the tensile the delayed hydrogen cracking test or the surface stress cracking test. The sample will be loaded in a tensile stress. So if we assume the tensile stress is 1, because we know the Young's modulus, then we will know the distribution of the elastic strain in a certain area. Yeah, so we can compare the elastic strain map and the hardness map, and we can find some regions with both high elastic strain and high hardness. Such regions must be very susceptible or more susceptible to the hydrogen-assisted cracking. Yeah, next several slides, I will introduce some updated results of the delayed hydrogen cracking test. First, we use the Glebo simulation to produce a heat affected zone in a base metal sample. This is a base metal sample. This is a sample with a heat affected zone, high hardness heat affected zone in the middle section. We then do the Postweld heat treatment on the sample to reduce the hardness in the heat affected zone. This is F22 steel. This is the 8630 steel. We try the different Postweld heat treatments and decrease the hardness and also decrease the hardness for the 8630 sample. Then we cut the samples into dog bone shape and installed into the delayed hydrogen cracking test frame. The load of the DHCT is 90% of the yield strength. The solution is a sulfuric acid solution, and the sample is immersed in the solution, and the hydrogen ion the sample as the cathode was charged at 10 microamp per square centimeter, and the hydrogen ions in the solution will migrate to the surface of the sample and to form the hydrogen atoms or hydrogen gas. The hydrogen atoms, parts of the hydrogen atoms will penetrate into the sample to promote the hydrogen-assisted cracking. The sample will crack after a period of time, and then we record the time to failure. Here shows the results of this time to failure. This is the Holloman-Jaffe parameter. As the Holloman-Jaffe parameter increases, the time to failure increases very rapidly. Yeah, the hardness goes down linearly with the Holloman-Jaffe parameter. We can also plot the time to failure with regard to the highest hardness here. Then we can see as the highest hardness in the heat-failure zone goes down, then the time to failure goes up. So we can imagine as the hardness 250, the NACE requirement, the NACE criteria, the time to failure could be very high, maybe hundreds of hours. Then we go to the conclusions. The first one is the type 2 grain boundaries and the solidification grain boundaries were found near the fusion boundary. Second, the highest hardness in the heat-failure zone of dissimilar metal weld samples is up to 430 HV. Third one, the hardness of 8630-625 heat-failure zone decreases linearly with the increasing Holloman-Jaffe parameter. F22-625 heat-failure zone has a secondary hardening effect at a certain tempering condition. The nano indentation gives higher resolution of the hardness line and the map. The hardness peak is revealed on the edge of the fissionless Penanogorsk zone as the initiation location of the cellular dendritic region, not in the Penanogorsk zone. The nano indentation can also measure the Young's modulus distribution and also produce the elastic strain map, which can help us to determine the location most susceptible to the hydrogen-assisted cracking. The last one is for the 8630 samples with the simulated heat-failure zone. The time to failure increases rapidly with the heat-failure zone hardness approaches 250 HV, the NACE criteria. Future work includes the delayed hydrogen cracking test on the F22 base metal samples with Glebo simulated heat-failure zone. Delayed hydrogen cracking tests on the dissimilar metal weld samples after different post-weld heat treatment. And 4-point bending surface stress cracking tests on the dissimilar metal weld samples after different post-weld heat treatment. And fractalography work on the failed samples or the fracture, and all the results will be analyzed and the conclusions will be made for the final presentation, for final dissertation. Yeah. That's all the presentation. Thank you.